Oh, wait, what's mine?
Are you eating again?
Hey, it's my lunch break. Besides, I'm reading up on the DRBIII dual-channel lab scope, so it's food for thought.
Well, good. I got a vehicle I need you to look at. It could be a tough case.
And what's the problem?
The customer says only that it hesitates intermittently, and there are no trouble codes set. It might be another ghost hunt.
Well, I'm not going to tackle anything like that on an empty stomach.
Okay, so pick up the RO and the keys when you're done. And this time, save me a cookie.
Yeah, right. I guess I better read the rest of this. I have a feeling I'm going to need it.
A couple of months ago, the June MasterTech introduced you to the features of the new multifunction PEP module for the DRBIII scan tool. In this month's program, we'll be taking an in-depth look at the dual-channel lab scope. You may recall that the scope's two separate channels allow simultaneous monitoring of two different component signals. We'll begin with an overview of digital storage lab scopes, including when you need to use one. Then we'll discuss the general characteristics of lab scopes and the features of the DRBIII dual-channel lab scope in particular. We'll also cover the setup, options, and function keys of the dual-channel lab scope, as well as recording scope events. Then you'll see how to distinguish a typical sensor signal from one that appears abnormal and warrants further investigation. And finally, we'll return to the drivability problem described earlier to see how knowledge and use of the dual-channel lab scope can be a great help in the diagnosis of drivability problems. If you've been troubleshooting drivability for a while, you may have used an oscilloscope, like that found on a tune-up machine. These units were used mainly to check secondary ignition patterns. There are limitations to standard oscilloscopes, however. In addition to being large and cumbersome, they may not capture intermittent problems well enough for diagnosis. These limitations, coupled with the spread of onboard electronic control modules, produce the need for smaller yet more sophisticated electronic test tools that are also easy to use. That's when digital storage oscilloscopes, which are also known as lab scopes, came into the picture. In addition to displaying many types of component signals, these tools provide many advantages over their predecessors. Digital storage oscilloscopes sample data several thousand times per second, giving an extremely accurate data display without missing the tiniest glitch in the signal. Other tools, such as digital multimeters, don't sample the signal nearly as fast, and the data is averaged before it is displayed. This could lead to the tool and its users missing a rapid change in the signal. There are other benefits to lab scopes as well. They enable the user to see exactly what the PCM is seeing and doing. This can help differentiate between component and controller problems. Lab scopes may also be useful when a drivability problem exists, but no diagnostic trouble codes are set in the PCM's memory. And many lab scopes feature an automatic setup, which makes setting up and using the scope a snap. Considering all the advantages that lab scopes provide, it's easy to see why Chrysler added the dual-channel lab scope feature to the DRBIII. Now let's talk about some general features of lab scopes. Then we'll see how the DRBIII lab scope incorporates those features into its operation. You can think of a lab scope waveform as a graph of voltage over time, plotted on a grid of screen divisions. The lab scope samples the signal and plots each voltage level on the vertical axis as the signal changes with time, which is shown on the horizontal axis. The signal is sampled thousands of times per second, and the waveform is displayed as a continuous trace. In order to view the signal, the values of the voltage and time divisions can be adjusted. Of course, lab scopes must have at least one channel for signal input, although many lab scopes feature two channels. Lab scopes can display several different types of waveforms, including a single trace, slow changing signal, a square wave, which alternates between two voltage levels, and pulses, which are repetitive signals that spend more time at one voltage level than another. Lab scopes also display sine waves that are produced by AC generators. A sine wave is a waveform that alternates its voltage level equally above and below 0 volts. Now that we've seen the general characteristics of digital storage lab scopes, let's look at the specific features of the DRBIII dual-channel lab scope. The DRBIII lab scope in the dual-channel mode samples data 20,000 times per second, which is about once every 50 microseconds. By comparison, the MDS data recorder samples vehicle data about 500 times per second. The PEP module on the DRBIII has 2 channels for the lab scope, which allows you to display and analyze waveforms from 2 different components simultaneously. The screen on the DRBIII is divided into 5 divisions vertically and 7 divisions horizontally. When the ×1 probe is used, the volt per division can be adjusted to 6 different settings that range from 200 millivolts to 100 volts. The time per division can be changed to settings between 4 seconds per division down to 0.4 of a millisecond per division. The dual-channel lab scope features an automatic setup option that adjusts the voltage range, time, and trigger according to the incoming signal, which is particularly useful if you're not sure of the characteristics of the signal you want to monitor. You can also set up to record waveforms with the DRBIII lab scope during test drives, which helps greatly when attempting to isolate the cause of a drivability problem. The recorded scope event can be reviewed in detail at a later time, which increases your chances of finding out what's wrong with the vehicle. We'll be taking a closer look at each feature of the dual-channel lab scope later in the program. But now, let's go over the accessories that are used with the lab scope. The 2 scope input cables plug into the DRBIII at the connectors marked CH1 and CH2. Then the cable to probe adapters twist on to the scope input cables. And the test leads plug into the adapters. You must use the ×10 adapter and probe when checking oxygen sensor signals and other low current sensitive circuits. This adapter adds circuit protection by increasing the resistance from 1 million ohms to 10 million ohms, or effectively multiplying the voltage by 10. As you probably know, oxygen sensor output voltages range between 0 and 1 volt. Be sure to use the ×10 cable in place of the red test lead, and remember to connect the ground clip to ground when checking O2 sensors. Your PEP module accessory kit also contains a 2-foot jumper wire with alligator clips on both ends. In our next segment, we'll go over the setup, options, and function keys of the dual-channel lab scope. But first, try answering this review question. The dual-channel lab scope samples data about how many times per second? A, 500, B, 20,000, or C, 1 million? The correct answer is B. The DRBIII dual-channel lab scope is a digital storage oscilloscope which samples the incoming data 20,000 times per second. Now that we've covered some lab scope basics, let's go through the setup and use of the DRBIII dual-channel lab scope. First, connect the scope input cables, the cable to probe adapters, and the test leads to the DRBIII. You'll also need to connect the power cable to the scan tool. An important point to remember is that if you use the power cable that plugs into the vehicle's cigarette lighter, you must use the black test lead to supply a ground. However, if you use the power cable that connects to the 16-way diagnostic connector, a ground lead is not needed, but still may be used. Once the DRBIII is booted up, select the DRBIII standalone option from the main menu. At the standalone main menu, select Option 5, Dual Channel Lab Scope. At the Scope main menu, select Live Data. This brings you to the Scope Setup screen. The Scope Setup screen features 10 options that program the display for the incoming signal on each channel. This is also where you choose to view the signal on a scope or meter display, or both if you wish. Select the channel you want to use for an option using the arrow keys. When the appropriate channel is highlighted, push F2 for a scope display and F4 for a meter display. press the F key again to deselect it if necessary. Then press F3 to enter the live data mode. The dual-channel lab scope has 4 different display modes, depending on how you set the display in the scope setup. The display shown here is the same channel, split scope, and meter screen. It shows scope and meter displays for the same signal. If you choose only the scope display for one channel, the DRBIII will display the scope grid full screen. The single meter screen display looks like this, similar to what you might see on a digital multimeter. The separate channel split scope screen is perhaps the most useful display. It shows you the waveforms of 2 different components at the same time, which facilitates comparison of the signals. With the different ways of displaying signals, you can see how flexible the DRBIII dual-channel lab scope is. The programmed screen displays also make it easy to use. If you want to check different types of signals, or you just want a fast way to start reading any type of signal, you'll find that the automatic setup is the best choice from the scope setup screen. The auto setup option sets the correct voltage range, time, and trigger for the incoming signal. For fast changing square waves of up to 5 volts, the 5-volt square wave option will fit the bill. This option is useful for reading the waveforms of components like the crankshaft position sensor and the camshaft position sensor, among others. The 12-volt square wave option should be used to display square waves that are greater than 5 volts, such as the PCM control of generator on time and the EVAT canister duty cycle purge solenoid. The 5-volt sensor option shows the waveform of relatively slow-changing analog components. This option can be used to display the signals of many sensors, such as the throttle position sensor, the engine coolant temperature sensor, and the intake air temperature sensor, among others. When you want to view the signal of a component that generates a sine wave, use the AC voltage option. The lab scope will display the voltage level alternating above and below 0 volts. Components that produce sine waves include transmission output speed sensors and turbine speed sensors, as well as wheel speed sensors on vehicles that are equipped with anti-lock brakes. When you need to see the signal generated from an O2 sensor, choose option 7, the O2 sensor display. Remember to use the ×10 probe when reading oxygen sensor signals. Poor grounds can also be a cause of intermittent drivability problems. So that's why Chrysler included a ground setup for the dual-channel lab scope. This option will also help detect excessive noise on the ground circuit. This feature uses the ground path from the vehicle's battery through the PCM to the 16-way connector and the DRBIII. Select option 9, injector pulse width and ignition primary when looking at fuel injector patterns, or for any primary ignition signal that has inductive spikes. You can also use this option to check relay operation. The last program display option is the generator ripple. This display helps you analyze diode outputs. So that's how you set up the scope to display signal waveforms in the live data mode. Once you have a signal displayed on the DRBIII, there are many options and features to help you analyze it. Let's take a look at them. As we told you earlier, the DRBIII screen is divided into 5 divisions vertically and 7 divisions horizontally. To calculate the volts per division, divide the voltage range by 5. If the signal displayed on the lab scope won't fit on the screen, the DRBIII alerts you to change the voltage range by displaying an over or under indicator on the right side of the scope display. The voltage range is adjusted using the F2 voltage function key. From the voltage menu, use the Enter key to highlight the range. Then use the arrow keys to adjust the voltage range. The time per division, or time period, is adjusted using the right and left arrow keys when the time period is highlighted. The signal display can be frozen at any time by pressing the Read-Hold key. This can help you to analyze the signal in depth. To return to the active display, press the read-hold key again. The meter display also gives you indicators to help you along. These include the active channel, the active data numeric value, and the active data option, or which program display you selected from the scope setup. The meter display also shows the minimum and maximum data levels. You can reset these values by pressing the Yes key. We've touched on some of the uses of the function keys when operating the lab scope. Now let's look at them one by one. The function keys provide access to all of the scope options, and pressing one brings up the menu of still more functions. By pressing F1 at any lab scope screen, help that's related to what's on the screen will appear to guide you through any problems you may encounter. To return to the live data display, press the F1 key again. The F2 voltage key is one you'll use quite often while analyzing signals on the lab scope. Let's go over the functions and when to use them. Pressing the F2 key at the live data display brings up the voltage menu. Use the Enter key to highlight each option and the arrow keys to change the setting. The channel heading appears on the left side of the display. Any changes you make to the display will affect the active channel. So if you have two channels displayed, select the channel you want to make adjustments to with the arrow keys. The next option on the voltage menu is the AC or DC coupling setting. This should be set to DC unless you are looking at AC sine waves. If you're using the ×10 probe, you'll need to adjust the probe setting on the data display. To do this, select the probe setting and adjust it to ×10. Otherwise, leave the probe setting at ×1. We've already talked about adjusting the voltage range on the data display, but you should be aware that when the probe is set to ×10, the voltage range is also multiplied by 10. This means that the voltage range can go as high as 1,000 volts as far as the display is concerned, but we don't recommend trying to view any waveforms on a 1,000-volt circuit. The last item on the voltage menu is the offset. This setting determines what part of the voltage range is actually displayed. The default setting is 4 divisions above 0 and 1 division below. The offset is adjusted 1 division at a time by pressing the arrow keys. Pressing F3 at the live data display will call up the trigger menu, which sets conditions that must be met in order for the waveform to display. The 4 trigger settings are auto, normal, single, and manual. When the trigger is set to auto, which actually means any trigger point, any signal detected is displayed. A normal trigger setting will display the waveform only if it meets voltage and position criteria that are determined by the level and position settings. It's like saying to the DRB, only display the waveform if it crosses a certain point on the display grid. When the trigger is set to single and the waveform crosses the trigger point, the signal is displayed and held. You can save the recorded signal for later playback by pressing the Yes key, or reset the trigger by pressing Enter. In addition to voltage and time trigger conditions in the normal and single settings, you can select the trigger point to detect a rising or falling edge. This synchronizes 2 different repetitive waveforms to help you compare them. Set the trigger to manual if you should need to capture and hold any signal detected by the lab scope. Any trigger point is set, and any signal detected will be displayed and held. Save the recorded signal by pressing the Yes key. The DRB labels scope events recorded with a single or manual trigger with a date and time of the recording, which is taken from the DRB's internal clock. You'll see how to play back recordings in a moment. The last function key is F4, which allows you to adjust the data display's cursor function. Positioning the cursor is like telling the lab scope to display the difference in voltage, time, or frequency between 2 points on the waveform. When the cursor menu is displayed, choose the type, and you'll see a pair of horizontal lines for voltage or 2 vertical lines for the time and frequency setting. Use the arrow keys to specify a start point and the offset or end point. The difference between the cursors you position is displayed under the delta heading, which also updates as you change the start point or offset. To play back scope event recordings made in the service bay or on road tests, you need to go to the Recorded Events menu. You'll find a list of scope recordings by selecting Recorded Events from the Scope main menu, then selecting Playback from the Recorded Events menu. Use the More key to change pages of recorded events. Select an event for playback by highlighting it with the arrow keys. Then press Enter to play back the recorded event. While the event is displayed, the function keys operate the same as in the live data mode. A horizontal line at the top of the display represents the entire signal saved in memory, and the brackets show the portion of the signal that is visible on the screen. Use the right and left arrow keys to view different parts of the recorded signal. When you no longer need an event, delete it from the recorded event list. Press Yes to confirm the event you want deleted. Now that you know how to use the dual-channel lab scope, we'll learn about the differences between typical and abnormal signals in our next segment, right after you answer this review question. The setting that determines which part of the voltage range is displayed is the A, offset, B, cursor, or C, coupling. The correct answer is A, the offset, which is found under the voltage menu and is adjusted with the up and down arrow keys. So now you know all about the dual-channel lab scope and how to display signal waveforms. But do you know what to look for once the signal is displayed? It would be impossible to show you all the variations in signal patterns that you may encounter, but we can take a general look at typical signal patterns produced by common automotive components during normal operation. It stands to reason that before you can pick out a faulty signal, you should have an idea of what that signal looks like when there are no problems anywhere in the circuit. When it comes to 5-volt sensors, such as throttle position, engine coolant temperature, or intake air temperature, to name a few, a typical signal will be relatively steady and slow changing, depending on which part of the drive cycle the signal is captured from. The voltage level should be within specification for the sensor, and not more than the 5-volt reference supplied by the PCM. An abnormal 5-volt sensor signal may exhibit rapid fluctuations, the result of an intermittent short to power or ground, or a momentary open somewhere in the circuit. The most common causes of these abnormal waveforms include damaged connector pins and frayed wires, corrosion, or a faulty component. A typical square wave, whether a 5 or 12-volt signal, looks like this. There should be 2 voltage states, high and low. Signs of an abnormal square wave include a signal that stays high or low too long, spikes on the top of a waveform, or a portion of the signal that does not pull down to ground or pull up to the reference voltage. There are many conditions that can affect circuits that have square waves, but some common ones include shifted grounds due to corrosion or other wiring faults, faulty components, and in rare cases, a controller problem. When a component, such as the crankshaft position sensor, is faulty, it may generate an abnormal square wave, which could lead to any number of drivability problems, like misses, die-outs, and other symptoms. A typical sine wave should be symmetrical, with the voltage level above and below zero being equal. The type of sensor that generates the AC sine wave will also have an effect on how the sine wave will look. A permanent magnet sensor, such as those used as wheel speed sensors, should produce an even, rounded sine wave. Sine waves that exhibit uneven spikes or excessive noise should be investigated. It could be the result of a condition such as a broken tooth on the trigger wheel, improper gapping, or metal shavings on the magnet. Oxygen sensors that operate abnormally could be a result of either a problem in the oxygen sensor circuitry or of some other faulty component affecting O2 sensor levels. A normal fuel injector waveform is repetitive. The injector on time should drop close to zero, and the pulse width should reflect changes made by the PCM. You should look for voltage spikes of differing amplitude between injectors and any other differences between signals to flag a faulty injector. Damaged connectors, corrosion, and PCM problems can all cause abnormal injector pulse patterns and the accompanying drivability problems. Don't forget that a good ground is just as important as any other part of the circuit. The lab scope will allow you to check for stable ground with a pre-programmed ground option. The most common problems with a ground signal are caused by corrosion, intermittent continuity, and high resistance. This ground was measured between battery minus and sensor ground and rescaled to properly display the signal. The only way to become proficient at recognizing typical and abnormal component signals is through experience. By using the lab scope as often as you can, you'll soon be able to pick out suspicious waveforms, which will help you accomplish your goal of diagnosing and fixing the vehicle. We'll be putting the dual-channel lab scope to work on a sample problem, but try answering another review question first. On these two fuel injector waveforms, the top one is normal, but the bottom one could be caused by A, a leaky fuel injector, B, corrosion on the injector's connector, or C, an open injector circuit. The correct answer is B. The waveform shows low amplitude when the injector is shut off, which can be caused by corrosion on the injector's connector. In a lot of situations, the use of a lab scope is not really needed to find the cause of drivability problems. If the PCM is able to detect the cause of a problem, a trouble code will be set and the mill will be illuminated. Many times the problem is found quickly and is made without any real involved diagnostic work. In other tools, such as the MDS, can help you find problems quickly by displaying live and recorded signals. But there are more times than you realize that using the lab scope will speed up the diagnosis. The dual-channel lab scope can be used when the MDS is not available, for example. The lab scope also provides direct signal measurement, as opposed to signals that are processed by the PCM and read off the data link. The lab scope is also useful for narrowing down the problem to a specific area and for confirming a diagnosis made with other tools. And the fact is, the lab scope is the only way to find those problems that avoid detection from other tools. When you need it, you really need it. All right, now let's return to the drivability problem as described earlier and see the lab scope in action. A 1991 minivan with a 3.3-liter engine that intermittently hesitates on acceleration, but doesn't set a code. It could be 100 different things, but the lab scope will help narrow it down. As always, the first thing to do is test drive the vehicle and verify the condition exists. After a while, the minivan hesitates when taking off from a stop. Now our technician has to consider what conditions would cause a hesitation that is severe but would not set a code. The cam and crank sensors are a good place to start. He'll use the dual-channel lab scope to verify that the two sensors are working properly. The connectors of the cam and crank sensors are then back probed at the PCM connector. With the 5-volt square wave option selected, he sets each channel to scope display, then sets the trigger to manual in order to capture the symptom when it occurs. Then the vehicle is road tested again. When the symptom appears, he captures the cam and crank signals with a DRBIII. Back in the shop, he reviews the recordings for abnormal signals. But the cam and crank signals are normal at the time the symptom appears. Knowing that the map sensor has the most effect on fuel pulse width, he prepares to record that sensor's signal. The lab scope is set up to record the map sensor with a trigger set to manual. A normal map signal should be steady and relatively slow changing. Another test drive produced the same hesitation, and our tech recorded the event with the lab scope. This time, the recording revealed intermittent dropouts in the map sensor, which is definitely abnormal. A new map sensor is installed to see if a faulty one is causing the severe hesitation. A test drive confirmed that the symptom was gone and the vehicle was operating normally. The intermittent dropouts in the map sensor signal did not set a code because the engine RPM was above 1500, which is outside of the onboard diagnostic system's test range.
So, how'd you make out with the minivan?
Oh, it was a tough one, but I pinned it down. It turned out to be a map sensor.
The map sensor. Well, how'd you find it so quickly?
DRBIII lab scope.
Oh, okay. Hey, you didn't save me a cookie, did you?
What cookie?
Yeah.